Hello and welcome to Web Learning where knowledge is shared. Today in this video I would like to do something new that I never done before, and that's to join collaboration with all my viewers to build a very smart 7S battery with BMS and connection. In the market there are many different BMSs, each one is doing something else. Some of them are only for power protection, for charging or discharging or charging and discharging. Some of them also include a balancing mode between the devices. They're quite cheap, but they don't have any microcontroller, and you cannot communicate with them to get more information. There are some devices in the market that they contain everything that you need, even though you still need some devices outside. And there are some more expensive devices that you can connect a microcontroller to them. There are also some standalone devices that can do multiple batteries, and you can connect a microcontroller. But again, you cannot get all the information and you're missing stuff. And if you have a microcontroller with A to D and the information, why not do everything all at once? So in this video, I'll show some basics ideas that I have, and I would like you guys to join me and we'll together open a discussion and try to build the best BMS with the lowest cost possible. So let's take, for example, a 4S BMS, and of course we can scale it up after we do this. I'll take also a microcontroller. I use the STM32F042 because this one also has a USB port, so we can connect it also to a computer through the USB. But again, we can decide on any microcontroller, even a low-cost one, and then we can change it, as this is just a rough idea on how I see things. So we can use this just as a reference on how a BMS should work. We have a few batteries, 4 in series in this case. We have some type of a resistor that goes into a pin of the microcontroller to measure the voltage. We have some R-sense at the bottom, and we have some overcharge protection MOSFETs. Now, because the microcontroller can receive between 0 to 3.3 or whatever voltage is on the VDDA, we cannot push the 4.2 volts that comes from each battery. So first of all, we need to do some kind of resistor divider. So we need to put ground. We need to put some shunt resistor. Now we need to put some resistor dividers. Again, I'm only using simple resistors. We can disregard the value of each resistor because we need to decide after what will be the size of each resistor. In order for us to decide which A to D pins are free, it is best to use the STM32CubeMX. We can decide between the TSUB20 or the LQFP32 or the LQFP48. I would say let's start with the TSUB20 and see if it fits all the things that we need. So let's try to use all the communication things that we need in order for this to work. Now the USB is not working, and if I hover it says swap pins, go to sys. So I'm going to sys, I'm swapping pins, and I have the USB. So let's choose a device. Now I don't need the CAN bus. I will probably need SPI, and I might need an I2C. This way we have different ways to communicate, but maybe not I2C because I2C is a master, and with the SPI you can chain them. Let's see how many ADCs we have. 1, 2, 3, 4, 5, 6. So up to 6 cell, this will work fine. More than that, we'll need to find a different microcontroller. We only need 4 for the 4S, so PA0, PA1, PA2, and PA3. and we have some GPIOs left for the other things. We can see that PA0, PA1, PA2 and PA3 are free. We'll copy the net. Going back, we have USB DP and USB DM, PA12 and PA11. You can see that PA12 is USB DP, so positive. So PA12, it goes to the top positive because the naming is under the pin. We need ground, and that's it. For the UART, again, I'm going back here. Asynchronous is conflicting with ADC in 3. So let's disable in 3. And asynchronous is working. So we need to change this to in 4. And the UART, so RX is PA3. And one is TX, PA14. We want also SPI. SPI are 3 pins. For now we'll take a header with 4 pins, but at the end we'll use 3 pins. And again, as before, PA7, 5, 6 and 7. And we'll change the name accordingly. Okay, now because we need to debug the device, we cannot use the UART. Let's see if I remove in4 and in2, if this will help. And now I'm left with in4 and in9. And that pretty much covers a 4S battery. Now we need to move in2 to PB1. So PA2 is the TX, PA2 is the TX, PA3 is the RX, and PA13 and 14, that's for the debug. This is the SWD. Well, of course I'm having a mistake here because I'm using a bigger device, but it doesn't matter because it's the same code and everything is the same. Let's see if we have it in a small package. Again, we can use the same pins and everything. PA2, PA3, PA4. We are missing the shunt measurement, so this will not fit. The 20 pin will not fit. This is a 28 pin. I'll quickly import the project. Okay, everything is set correctly. Now the USB is not working. Okay, we got this done, and we have more pins free. SPI is set on full duplex. CCC, we have debug 0 wires, and everything is okay. Now let's do in 3. And let's make sure that everything is correct. So in 0, in 1, in 3, and in 4. We need to add a MOSFET, and of course there are other and reset and VDD and the rest of the stuff for the microcontroller, but we leave it after. We'll see how we can do this with an LDO, or maybe with one of the batteries connected to the first battery or something. So how do I see this working? First of all, we can measure each voltage of a battery because of the resistor divider. So we can actually measure the voltage on each battery. Because we know the measurement of the shunt resistor, we can measure also the capacity on each battery, because the current on all the batteries will be the same because they're in series, times the voltage of each battery. We are able to know exactly what is the capacity for each battery. To protect the complete battery on or off, we can go back and decide on any one of those pins to be a GPIO output. Now, why do I have the SPI communication? The idea is to have few boards connected in parallel. So the way I see this is each device or each BMS, so this is a complete, for example, 4S BMS plus microcontroller. Each one will be a 4S microcontroller. We'll transfer the data to the next device, to the next microcontroller. And as you can see, we have an SPI on each device. The data packet can be something like, now this is the packet that's built on the first one. The second one, the microcontroller, when he receives the data, what he will do can go on each microcontroller with the same software, will do the same thing over and over and over again. So at the end, you'll get, if we have four BMS, so we'll have D4, comma, B1, A1, blah, blah, and then D3, comma, V1, and everything, and then D2, and D1. So the software will be always the same, and whatever data that will come in, it will buffer it, and it will relay it forward with the number n+1. So at the end, we'll know exactly how many BMSs we have. The smallest number is the closest to the PC. The largest one is the furthest to the PC. Let me do a short list of all the ideas that I had right here, and let's go through each one. So let's go through the list that I did. So to update using SPI and copy internal flash to the next one, this is what I showed down here on how to update each data forward. SPI communication between microcontrollers, because they have a dual way to upload and download information, and this is synchronous data, so we don't need any accurate crystal or something for the high-speed data. This is much more easy. We can add also to this data except for the voltage and current for each battery. We can say if the information, if the battery is discharging or if it's charging, or there is no change in the data, or the battery is bad. The last microcontroller is a USB, so we said that we'll do that. We can do voltage control, so we can know exactly what is the voltage to each device. Plastic using 3D printer, we can also build a plastic case for this. Sleep between readings, so the microcontroller doesn't have to be always on. Let's say if we measure every second, then we can put the microcontroller in sleep. That will save also a lot of energy. Stop when not used, using resistor in the analog watchdog timer. Using resistor in the analog watchdog to see the changes greater than 0. Wakes up every 1 second. So again, we can use a mechanism on the voltage to see if there is any change on the batteries. So if there is no change on the shunt, for example, so it means that there is no current that's being drawn and the system can be dormant. We can set the microcontroller to stop at 2.5, so looking at the voltage of each battery, we can decide what voltage it is, and then we can start working again when the batteries are being recharged. Small LDO from the 4.2, again we can use 4.2 from here, using an LDO to control the microcontroller. A shunt resistor, we added this. Internal pull up on the GPIO to SPI and external pull up. This was an idea that I made to decide if the communication is just the USB or the SPI, but again it takes more pins, it doesn't really matter. The last thing is the Git folder, PC software, software update, chain, and the main BMS. So there are a few things to do here. One is the actual design of the board. So I saved this project. So I'm sharing this document at the link below. You can see what I wrote and the design. You can see for now the BOM that I've used, but those are very simple parts. There are no attachment. And I left here a place to comment. So any comment that you have for the design, any idea that you have for this schematic, when we'll start doing the PCB design, any comments, let's write them here, and I'll start doing it. After I see some collaboration, maybe I'll add also some members to help me with the design itself. Also for the GitHub, I opened a folder for the code. I can tell you I don't know that much how to use GitHub. I read how to do things and how to open the project. If you have any comments on what will be the best way to do this, I will appreciate this. We'll do here in the GitHub the PC software and the software to update the chain and the main BMS. So we'll have here three folders. One folder is for the PC to see all the data coming in. We can do it as a picture, we can do it, whoever can help me in the PC program. The other software will be the actual code that we're going to do for the microcontroller. Let's use the STM32, the HAL, and the Atomic, so everybody can join in. And one thing that I want to do at the end of the BMS, after we do everything, I want to have an automatic update. So when we'll have a new code that's being generated, because the SPI has up and also down, we can push an update of the flash to the microcontroller, and this will push it forward to all the microcontrollers. So from the PC software, let's do here a PC. So from the PC side, we'll be able to push back a software update to all our BMSs. So thank you for this. Let me know what you think. One comment we can do also some load balancing. Let me know what you think, and thank you for everything.